Hi, I'm Chandla Maheva, and through this tutorial, we'll be learning about QUIC. First, we'll be talking about what is QUIC. QUIC is a transport layer protocol, which is Quick UDP Internet Connections developed by Google to improve the performance of Google's web applications. This protocol includes initiating encryption and the exchange of keys in the initial handshake process. It also only takes one round trip to establish a path for communication. As you can see in this diagram, when initiating a connection through TCP, it takes a complicated process of going back and forth to create the connection. But as you can see in here, when creating a connection through QUIC, it takes only one round trip to initiate the connection and send the packets. Also, when transmitting packets to QUIC, the first packet sent by QUIC can transmit application data right away and contains cryptographic data, unlike TCP, which needs the handshake to be established first. Also, QUIC is built on top of UDP but contains similar features to TCP, such as congestion control, packet transmission, multiplexing, error correction, and many more. Reduced latency and built-in transport layer security, which is TLS 1.3, makes QUIC more reliable. TLS 1.3 is the most advanced transport layer security currently available. So it makes using QUIC more safer. And next we can be talking about key functionalities of QUIC. The key functionalities of QUIC is faster connection establishment, stream multiplexing, packet transmission, error handling and loss recovery, and congestion control. The QUIC establishes a connection faster by using a combination of encryption, key exchange, and transport handshake. The stream multiplexing in QUIC allows you to transmit several data streams over a single connection, and each of these streams are independent from each other. So a packet loss that happens in one stream doesn't affect any of the other streams. Then packet transmission, and each packet has the capacity to carry one or more frames within it. Frames are such as stream and ping, ACK, and many more. Then error handling and loss recovery. When a packet loss happens within QUIC, QUIC increases the retransmission rate rather than decreasing the transmission rate to recover lost packets. This improves the performance rather than decreasing the performance when packet loss happens. So, and then there's congestion control to control congestion and minimize congestion within the QUIC. Next, we can talk about the frame formats within QUIC. There are many frame formats within QUIC, but few of them are stream, ACK, crypto, ping, datagram, padding, and there's many more. First, we'll be discussing about stream, ACK, crypto, ping, and datagram. Stream carries application data on a specific stream and includes the stream ID, offset, length, data, and flag fields. ACK for frame format acknowledges the received packets and includes the fields such as largest acknowledge, ACK delay, ACK range, and ECN counts. The crypto frame format carries the cryptographic handshake messages and includes frames fields such as offset, length, and crypto data. The ping frame format is used to maintain a connection during periods of inactivity or is used to verify the connection is still active. Then we have the datagram format, which allows application data to be sent in an inconsistent and unordered manner and includes the fields, length, and data. And then we can talk about the advantages and disadvantages of QUIC. First, we will talking about advantages. The lower latency due to the zero round trip time to establish a connection makes the QUIC much faster than TCP and UDP. Also, the congestion control and the packet loss and recovery mechanisms used in QUIC make sure that performance does not deteriorate in high packet loss networks. Then we have the multiplexing of QUIC, which allows multiple streams of data transmission in one connection, which also makes the packet transmission faster. Then we have the retransmission and forward error correction features, which enables it to recover from packet loss more quickly, improving the reliability of QUIC. Then we have the built-in security, which is TLS 1.3, which makes using QUIC much more secure and reliable. Then We can talk about the disadvantages of using Quick. Even though there are many advantages that makes uh, using Quick very beneficial, there are still a few disadvantages that we can improve to make Quick more reliable and faster. Then we have implementation complexity. Quick requires modifications to both the client and the server, which makes the implementation of Quick more complex. This is a disadvantage as it may take more resources to implement a quick transport layer protocol. Quick may also require more CPU and memory on the client and server due to its more intricate protocol logic. Also, Quick is a newer transport layer protocol, so there can be compatibility issues where older models that of devices cannot use Quick. So then there's Quick's usage of UDP. Certain mailboxes such as firewalls and NATs may restrict or stop Quick communication due to using UDP. Also, the Quick has an increased processing overhead, which is also a disadvantage. Next, we can talk about network applications in real world that use Quick. Google is the developer of Kik, so Google services such as Google Chrome, Gmail, and YouTube were the first to support and use Quick. Among them, Chrome was one of the first web browsers to include and support Quick. The recent version of Hypertext Transfer Protocol, which is HTTP 3, uses Quick rather than TCP to operate because of the reliability and the secureness of Quick. A few of the current web browsers that support HTTP 3 includes Microsoft Edge, Mozilla Firefox, and Google Chrome, and this indicates that websites that are delivered via HTTP 3 are using Quick. Meta is also using Quick to improve performance, and this includes services provided by Meta such as Facebook, Instagram, and WhatsApp. To improve the efficiency of file sharing and video conferencing, Microsoft is also using Quick in Microsoft Teams and Office 365. Fortnite, which is a multiplayer game that is very popular among this generation, is also using Quick to lower the latency and boost the data transfer reliability. Next, we can analyze the quick packet transmission using Wireshark. We need to start capture by clicking start capture, and then we go to a website that uses Quick as a transport layer protocol, which we can use YouTube. And if we load the YouTube and then visit a video, then we can go back to the Wireshark and stop packet capture. Now we can analyze the quick traffic by applying the quick traffic filter by clicking here, and then we can see at the start CryptoFrame contains cryptographic handshake messages, includes offset length and crypto data, and then we can see padding and ping frames. The ping frame is used to check if the connection is still alive. It's a simpler frame without much additional data. And then we can see the ACK, which is the acknowledgement frame, which acknowledges the receipt of packets, includes fields like largest acknowledge and more. And then we can see here this says handshake and this says 0 RTT, which means it has taken 0 round trip time to make the connection. And here it says SCID. SCID is source connection ID. The source connection ID is used to identify the connection from the sender's perspective. And then you can see here DCID, which is used to route the quick packet to the correct connection on the receiving side. And this is the initial, which means it's initial delicious connection. And if we analyze the crypto frame, we can see that it is using user datagram protocol, and we can see the source port and the destination port. And then in quick, we can see that the packet length is 1250, and then we can see the destination connection ID. Then we can see that there's only one packet that's been sent, and then we have the payload here. And if we check here, you can see that the handshake protocol is the client hello. And then if we go here, we can still see that it's using the user datagram protocol, and then we can see the packet length here and the connection ID and then the payload here, and we can see all the frames that have been sent using in Wireshark, and it also says handshake protocol client hello. And then if we analyze the acknowledgement frame, it still uses the user datagram protocol and the source port and destination port we can see here. And then we can see the source connection ID, and then we can see the length, which is 1232, and it contains the largest acknowledge, acknowledge delay, acknowledge range count, and first acknowledge range fields. Then we can see the padding length here, and that's all for the acknowledgement. And if we check this handshake in SCID, and it contains the source connection ID and the payload, and it is the frame type crypto, which means it's encrypted. And then we can see that the remaining payload is shown here. And then we have protected payload that we can analyze. So you can see there's packet length, which is 531, and it also includes the checksum status. And then we have initial, then we have handshake, and we can analyze all these packets sent by Quick to analyze the Quick packet transmission. Now we can discuss about security threats associated with Quick. A key issue of using Quick is standard network security like firewalls are not able to distinguish between Quick traffic and other types of communication. Thus, network security is jeopardized as firewalls are less successful at identifying incoming threats through Quick. However, because of the inbuilt TLS 1.3, this issue can be minimized. Quick is also vulnerable to amplification attacks since it uses UDP. Also, state exhaustion attacks are also a security threat that can put the network security at a risk. By making numerous connections, attackers can possibly exhaust server resources. We can mitigate these security threats associated with Quick by setting rate limits for communication attempts. Now we can discuss about the scalability of Quick. Quick is engineered to exhibit scalability in a variety of network scenarios. It is appropriate for large-scale installations such as content delivery networks and cloud services because to its sophisticated congestion management methods and capacity to accommodate many streams inside a single connection. Also, in real world, AWS, which is Amazon Web Services, also use um, Quick due to its scalability and the reliability and secureness. And that's it for my tutorial. I hope that you are able to gain invaluable knowledge on Quick that will help you resolve network issues and help you develop and maintain adaptable, reliable, efficient, and secure web services. Thank you.